Okay, we're in section 15 of the notes, and I'm just going to go over to Sage Code. Yeah, I always say you got to look back over your notes. If you studied the section 15, you should realize that this material here applies to what we just covered in 15. All right, so I'm just going to go to Sage and type things in, reset. What does this do? It kind of gives me a clean sheet of paper. I'm going to say n is a variable. And then I'm going to say, this might seem strange to you. I'm going to tell Sage, please assume that that variable n now can only be an integer. Now, this is what's known as typecasting. So when you take computer science courses, a lot of times what you do is you typecast your variables. Some variable will be real, some, when I say real, float in typical computer science, or maybe it's integer, maybe it's a whole number, whatever. It's an integer. What does that mean? Could be 0, could be 1, -1, 2, -2, yada, yada, yada. And then I'm going to define a function, an. And that function is going to be, you know what? I'm kind of tired of typing. I'm going to start copy pasting. I'll put that down. And then I could, A1, it's pretty easy to type. I'll do that. It gives me 0. I could do A6, right? What's A6? Well, 37/15. And again, you should realize it's pretty easy to evaluate a function at a given value. All right. Now let's do this one over here. And again, I'll read it to you. And I'm going to just copy paste it though. It says sum, and then it says 1 divided by 100 times 2 to the nth power for n in 0 to 34. So what's it doing? It's doing a sum, right, of that term, which is 1 over 100 times 2 to the n, where n is going from 0 up to 34. So that's 0, 1, 2, 3, up to 34. By the way, this looks strange to me. This goes over your n, so it wants to approximate it, but it says digits equal 11. Let's see what happens. I'm going to get rid of the digits first, though. And it gives me that over there. So I'm going to say over there, at least I know what the number is. Let's go back and, whoops, sorry about that. I'm going to do this one again. And I want to see what the difference is. Well, what does it do? It actually just simply gives me a decimal number for it. And if you count the digits, let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 digits, right? Okay. What does the e to the 8th means? It means 10 to the 8th power. All right. That's that number right above it. All right. What number is better? I don't know. I think the one without the e in it's better. By the way, e does not mean Euler's number. E means scientific notation. That means times 10 to the 8th power. Let's put the next one in. We'll talk about it. I'm just copying it, but I will talk about it. And it has something to do with what we've been doing. All right. Now, whether it's something we've done in lecture, something we've done with the examples, or something that you've done with homework possibility now or in the future, it has something to do with it. What does it want to do? It wants to do the limit as, and I'll read it to you, of this ratio, which is 1 minus, that's Euler's number to the minus n, over 1 plus Euler numbers to the n, as n goes to infinity. Let's see what happens. And it says it's equal to 0. All right. I guess we did that limit. Now let's put this one over here. A little more complicated. When I say more complicated, not to type it, to understand it. And what's this one to be? -1 to the nth power, where n is going off to infinity. All right. So what's it going to do? It's going to bounce back and forth between plus or minus 1. So, looking at it, it should be d and a. Oh, IND, right? I guess that's a way of saying, let's type that in, see if there's any information on that. No, it's not found. Anyway, I'm going to say that means they can't determine the value of it, which means it doesn't exist. All right. So let's take a look at the next one. Again, just a copy paste. I'll kind of look at this one over here. It's kind of a famous limit. It's 1 plus -1 to the nth power over n as n goes to infinity. Well, that should be 0. Wow, 0. We got that right. All right. Ooh, factorial. I think we've seen this one before, right? Put this one down. Oh, you know what? I didn't do this one yet. That's 11 to a power minus 1 over n. As n goes to infinity, that would be minus 1 over infinity, which would be 0. 11 to the 0 would be 1. Let's see. Wow, 1. Let's do this one over here. And I'm just copy pasting, which is really, I'm going to say a lot of students copy paste without reading it. And what's this one over here? 11 to the n over factorial n. And the bottom line is which one grows faster? The factorial grows faster as n goes to infinity. So it should be 0 as stated. This is a function now, an. Yep, I'm copy pasting. I'm going to do this one over here. And this has something to do with what we've done. Let me tell you what it says. It says solve. What's it solving? It says the absolute value of an minus 1, right? And we know what an is, less than or equal to 1/1000th for n. All right, let's see what it gives us. Wow, look at that. Right, look at that. All right. And again, that might seem rather confusing at this point, right? Rather confusing. So what I'm going to claim over here is I'm hoping you have some background to this over here. All right, some background. All right, what do you mean by background? You're looking back over this and you're wondering, can this be done by hand to make more sense out of what's producing over here? But again, you see over here, it's got and negative numbers and positive numbers. You know what I'm going to do? Let's just see if we can tweak the code a little bit. So I'm going to say assume n is now greater than 0. Let me try that code again. I'm getting a much better answer now, aren't I? And yeah, but I don't know why they put down the n is less than -9 again, because I said assume n is greater than 0, right? And they put that down. But anyway, what am I getting? That number, which I was expecting, that n would be greater than or equal to 89,9991, right? We've actually done that one before. Let's take a look at this one over here. Another limit problem. Like a copy paste. Let's see what happens. 0. Does that make sense? Yeah, I think we've done that one before, right? I think we've done that one before. And what am I saying? As n goes to infinity, the square root of n plus 3 and the square root of n look identical when you go towards infinity. So their difference would be 0. All right, let's do this one over here. Again, that OO is supposed to look like an infinity to me. What's this one over here? 1 plus 1 over n to the nth power as n goes to infinity. Boy, that's a recognizable one, isn't it? And what do I get? E. That's a defining feature of E. All right, that's something that was introduced in Math 119. Was it 119? Yeah, 119. You did logs of 119. All right, and that's a limit that you were asked to do in 119 by using a table of values. All right, let's do the last line of code. And what do you get over there? The limit is n times the square root of n squared plus 3 minus n. N goes to infinity. Here's another good one. All right, that's a struggle one, though, I'll be honest with you. That's a struggle one, yeah. So if we had to write that down on paper, I believe we've done that one already. I'd have to do that one on paper to get that limit. But let me see, square root of n squared plus 3 times n. Yeah, looks reasonable. Again, we would need to do that on paper if we really want to say that was a reasonable answer or not. What's the key thing over here is you're going to be typing in Sage code. You're going to be occasionally confused by it. The reason you might be confused by it is you did not do the groundwork. If you didn't do the groundwork, all input is going to look like garbage to you. The groundwork is so important. Let me repeat this. You are not going to get to the level of using a machine to solve problems unless you can do things by hand. All right. You got to do things by hand first. Then you're going to start to appreciate how a problem can be formulated and how a machine can help you with the problem. Thank you.